Now in this section we'll take a brief look at stochastic processes, and a stochastic process is ultimately just a random variable that evolves over time. Now we started out with random processes and random variables more accurately, and random variables are part of basic probability that we've covered so far. But what we haven't talked about is the random variable and how it evolves over time. More accurately, how often am I likely to get a certain value of a random variable? How often am I going to have an arrival in the case of a Bernoulli random process? How often am I going to have an arrival in the case of maybe a Poisson random process, which we'll look at here in a few weeks? And again, random processes really just capture that evolution of random variables over time. And so there's a couple key things here. The first is that we can use either discrete or continuous time. So remember that discrete time is when we're creating the time slots. We're saying these are my time buckets. So this is T1, T2, T3, and we're asking what happened inside each of these time buckets. Did I have an arrival or not? And this is a perfect example of a Bernoulli process. Now a Poisson process would ask the same question but in continuous time. So that is as these time buckets become infinitesimally small, as they approach zero. And so within these, a Poisson process really gives you a way to say at what exact time, at what continuous time did an event occur. Now, stochastic processes can be viewed in a couple of different ways, and we'll look at these right now through the lens of a Bernoulli process, just because Bernoulli processes are by far the easiest form of process to understand. And a stochastic process in a simple first view can really be looked at as an infinite sequence of random variables. That is x sub 1, then x sub 2, x sub 3, all the way up to x sub n, where n is approaching infinity, or maybe it's less than that depending on the problem you're trying to solve. And ultimately what we're interested in finding is first the expected value of a given random variable. So at a specific slot of time, what is the likelihood, what's the expected value that a random variable is a success, that specific slot is a success? And we find that right here through the expected value of x sub I being equal to p. And this just follows from the definition of the Bernoulli random variable. Now, the next thing that we might be interested in is, hey, what's the variance? How much variation should I expect in this process as we progress through time? And so we would say that the variance of the random variable x sub I, and again, this is the variance within a single slot of time, but the variance of the outcomes that we should expect is just p times 1 minus p. And again, that follows straight from the definition of the Bernoulli random variable. And then the last thing that we might look at is the PMF, the probability mass function of that random variable, again within that specific time slot. And so that would be here the PMF of x being p, where x is 1, and 1 minus p, where x is 0. So again, summarizing what we looked at previously, that the probability of success, or the probability of a 1, is just p, and then thereby the probability of failure of a 0 must be 1 minus p. Now, we can take this a step further and look at the joint PMF. That is the joint PMF of all random variables x. And since a stochastic process in general, again for the case of Bernoulli, is independent, we can say that this is simply the product, the multiplication of all of the individual PMFs on their own multiplied together. Again, this only applies because we've said that the random variables are independent in the case of a Bernoulli process. For some processes, variables may not be independent, and this equation may not apply. Now, a better view, or really just a secondary view of stochastic processes, is when we view them as a sample space. where our sample space is really the set of all possible infinite sequences of 0 and 1, or success and failure. And so we could look at that as maybe a time slot where I just get a 0, 0, 0, 1, 0, 0, or maybe instead that's 1, 0, 0, 1, 0, 1, and that another sample space or another potential outcome would be 0, 1, 0, 1, 0, 1, 0, or some series of those. And again, this would be every possible permutation would be our sample space here. And so we're looking at our omega, our sample space, as the set of all possible infinite sequences of 0 and 1. So if we say we're only looking up through k equals 8, then we would need to extend this out to an 8th digit. Again, all possible outcomes need to be considered because of our sample space. So as an example, let's say that we want to find the probability that x sub I is equal to 1 for all individual instances, for all of those i's. So another way to look at this is the sequence 1, 1, 1, 1, 1, and it's ones for infinity, or for all i's. And what we'll find going through some basic math and looking at our PMF of the definition of a Bernoulli random variable is that this is the product. It's the multiplication of the probability of success for however many iterations or i's we have. So let's say that this is the nth iteration. Then we would have that this is the probability that x sub 1 is equal to 1 all the way up to x sub n being equal to 1, and we would find that that is just p raised to the nth power, or p times p times p n times. Now, as n approaches infinity, it's important to note that this probability approaches 0, right? Because p must be less than 1, p to the n has to approach 0. The only way around this is if p is equal to 1, at which point it is a guarantee that you will always have all 1s from a probability perspective. You will have the probability of getting a 1 is all the time. So as long as this p, the probability of 1, is anything less than 1, then as n approaches infinity, this probability approaches 0. And this is kind of similar to continuous sample spaces because we're adding an infinite number of possible outcomes, right? We've said, again, that we can look at our sample space, omega here, as the set of all infinite sequences of zeros and ones, or of successes and failures. And so from that, as we increase the number of samples that we're taking, the number of elements in our sequence, as that number of elements approaches infinity, then there's really an infinite number of combinations, which means that the probability then approaches 0, because the probability of a specific outcome out of infinite outcomes is 0. And we looked at why that is back in the introduction to continuous random variables, so we won't go through that again. But just recognize that the logic here is kind of the same. Now, as a quick introduction, we're going to study several different random processes over this week, and then once we return from spring break, we'll look at 2 more. And these random processes are really going to be the meat of our third exam. But the 3 processes that we're going to look at are first Bernoulli processes, which we'll cover this week. And Bernoulli processes have no memory. That is, they have to be time independent. They do not know what happened in the previous time slot. And they are discrete time processes. So to be a Bernoulli process, there can't be any requirement for memory. In other words, each ith iteration has to be independent, and it has to be able to be bucketed in discrete time. Now, if you can't bucket in discrete time, but you can still maintain an independent process, then you can look at a Poisson process, and we'll go into a lot of detail on the Poisson process, which again is memoryless. It can't look back into the past to influence the probability of the next event. It has no memory. But it is a continuous time process, so we can look at that as infinite time or as continuous time to get an infinite number of possible time outputs. And then finally, there's also a Markov chain. And a Markov chain allows for memory and time-dependent processes. So if I have a random variable or a random process that changes based on what's happened, let's say that I have a random number generator that's not really that random and it's just generated 10 ones in a row and it says, oh, based on that, I now have to generate a 0. Then a Markov chain would be able to model that process for us because a Markov chain has the concept of memory dependence. Again, something that is not independent but dependent. So like I mentioned, we'll be going over all three of these different processes, the Bernoulli Poisson process and Markov chains, over the next several weeks in preparation for our third exam.